So I have here on the board a couple graphs. So the one on the top is K4, that's the complete graph on 4 vertices. So it's 4 vertices and they're all connected in all possible ways to the other vertices. And this one is it's the graph of a cube, right? So I've got the vertices and edges of a cube. And notice that the way that I've drawn them, right, some of the edges cross. So like these two edges cross in the middle here. Here, you know, these edges cross, these edges cross. Now on the one hand, right, we've said that the way that we draw a graph doesn't matter. There's still the same graph. It's still the same graph no matter how you actually draw it. All we really care about in terms of, you know, two graphs are the same if it's just the same vertices connected to the same edges. We don't care how it's drawn. But sometimes we do care about the different ways to draw a graph. So sometimes if a graph is modeling something in the physical world, you know, then maybe the actual way that you lay out the vertices and where the edges go actually matters. And in many of those situations, having edges cross can be bad. So for example, imagine that the edges are some kind of wires and we really don't want wires to cross over each other, or you know, or maybe the edges are like some kind of things we need to build and we physically can't have them cross each other, they have to kind of go around each other. Or, you know, a lot of graphs that you have that are modeling the physical world would naturally not have any edges cross. So for example, if you made a graph of all the states in the United States and you made a vertex for each state and you draw an edge between two states that share a border, then you're naturally not going to have any of those edges crossing. Just because of the way that the vertices and the edges are laid out, it corresponds to how the states physically are laid out in space. Okay, and so if we think about these graphs again, there's actually different ways we could have drawn these so that edges don't cross. So for example, this one I could redraw. I could move this edge. I don't have to draw it straight across the middle. I can kind of draw it around the outside. It's still the same vertices connected in the same ways, but now I've drawn it in such a way that the edges don't cross. And this one I could also put one square kind of on the inside. Make another square on the outside, right? So you can convince yourself that is the same graph, but I've drawn it in a different way. So the question is, when can we do this? Can we always do this? So it turns out the answer is no. There's some graphs that no matter how you draw them on a flat sheet of paper, you're always going to have some edges cross. So to see one example, there's a classic puzzle where I have 3 houses and 3 like utilities usually there. So like we'll say there's a water, electricity, and internet. So we'll draw it like this. And so what I want to do is connect. So each house has to be connected to each of the utilities, but I want to do it in such a way that the edges don't cross. Which, okay, I mean, this is a silly little puzzle. There's no reason that like your internet wire can't cross your water pipe. I mean, they can just go under each other. But for the purposes of this problem, we don't want them to cross. Okay, so let's see if we can do this. So I could go ahead and, I don't know, we might as well just like connect everything straight across. And then let's see, we could connect the water to here, and I can connect the water to this one like that, maybe. And then let's see, I need to connect the electricity, so I can connect it to this one. And then I could actually, I need to get to that house. I can't go this way and cross this edge, but I could go around here like that. So that works. Now I need to connect the internet. Let's see. So I need to connect it to, I can connect it to that house, right? Let's see. Can go like that. And I need, that's right, I need to get there. I don't think there's any way for me to get there. So actually, if you notice that like these edges here, kind of make this, those edges make this closed region, and this is outside of that, and this house is inside of it, and I can't, like, any way that I went, I'd have to cross over one of these green edges. And so, now, this is not a proof that it's not possible, because maybe I just made some bad choice early on, and should have made a different choice and would have been able to do it. But it turns out it's not possible. And you might like to think about, is there a way that you could argue why it's not going to be possible in general? But the point is, not every graph, like, there exists some graphs, so this is a good example of a graph where it's not possible to draw it without having at least some of the edges cross. Okay, so given a graph, you might ask the question, like, can this graph be drawn without edges crossing? And so graphs like that are called planar. So let's define that. So a planar graph is, or well, actually I'll say it this way. I'll say a graph is planar if it can be drawn in the plane without any edges crossing. Okay, and this is something that, as I mentioned, some potential applications. So this does have applications, but also it's just something that mathematicians studied because it seemed like an interesting question, and it turns out there's a lot of really deep mathematics behind this. So in general, it's actually really hard to tell. So if someone just gives you a graph, they just say, here's a graph, it has like 1 million nodes, and here's all the edges. Can you draw it in a way so that none of the edges cross? It's actually really hard to tell. No one knows of a good, like an efficient way that you could figure that out. But there are some things that we can say, and so there's various interesting theorems you could prove about graphs that are or are not planar. If a graph is planar, what properties does it have? And so we're going to look at one such theorem, which is really one of the most classic, and it involves Euler again. So Euler was definitely very involved in a bunch of stuff related to what we now call graph theory. So rather than, I'll introduce the actual statement of the theorem in the next video, but in this video, in the rest of the video, I just want to play around with some examples and see if you can figure out what's going on. So what we're going to do, so we're going to start with these example graphs. I want to count the number of vertices and the number of edges of each of these graphs, but I'm also going to count the number of what I call faces, because when they're drawn in the plane with no edges crossing, right, they naturally, it divides up the plane into different regions. So like, in this example, this is one region here, this green part. This is another region up here, and there's a region like this part in here, another region, and then we'll actually count, all this part out here as a fourth region. Okay, it's the whole plane is getting split up into regions. There's always going to be one that's like the infinite region on the outside. So we can count these, and in this case we have the number of vertices of this graph is 4. The number of edges is 1, 2, 3, 4, 5, 6. And the number of faces we just argued is 4. Okay? Let's try this one. So number of vertices is 1, 2, 3, 4, 5, 6, 7, 8. Number of edges is it's going to be 12, right? 4 around this square, 4 around this square, and then 4 connecting the two. And what about the number of faces? Well, it's going to be 1, 2, 3, 4, 5, and then one on the outside is 6. Okay, let's do one more example. I'm just going to make up some weird example. And in fact, I'm going to make up an example with like some loops and some multiple edges, because it turns out that the theorem works with any of those things. So I don't know. There we go. Sure. So the number of vertices here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of edges is going to be 1, 2, 3, 4. I have to be really careful here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I did that right. And you, of course, can pause it and make sure that you count really carefully and make sure that I got it right. Number of faces is going to be, let's mark these so that I, 1, 2, 3, that counts, right? 4, 5, 6, 7, and then 1 on the outside is 8. So try some examples of your own and see. So there is a nice pattern here. See if you can figure out a pattern and make some kind of conjecture about how these different numbers are related to each other.